Welcome back, AP Chemistry students, to Unit 7, Equilibrium. Today we will be talking about Unit 7.3, LeChâtelier's Principle. LeChâtelier was a French chemist and trained engineer who chose to teach chemistry because he had a great interest in chemical engineering, specifically that Haber process that we've been mentioning, the formation of ammonia, because ammonia is used to produce fertilizers, and if you could make fertilizer from the air itself, there was a lot of money to be made in that. So in 1901, LeChâtelier attempted to create ammonia from nitrogen and hydrogen gas at a high temperature and pressure, pushing those two reactants together. However, this caused an explosion and nearly killed his assistant, so he abandoned the project. It wasn't until much later that a chemist by the name of Haber came along and perfected his result. But we now know LeChâtelier originally came up with the idea to synthesize ammonia from nitrogen and hydrogen, and therefore we immortalize LeChâtelier with a commonly understood principle in chemistry that systems at equilibrium will work to stay at equilibrium. And it's kind of like you on a treadmill. If I were to come over to you and speed the treadmill up that you're on, you want to stay at equilibrium. You don't want to fly off of the back, so you have to run faster. Meaning that if you favor the forward reaction, the reverse reaction has to make up for that change. So a system at equilibrium is dynamic in constant motion and will stay at equilibrium unless a stress is placed on it. So a stress is me speeding up your treadmill. In a chemical standpoint, a stress is anything that favors either the reverse or forward reaction. So remember back in kinetics when we talked about speeding up a reaction, you could shift an equilibrium by causing something that made a reaction happen faster or favored the formation of reactants. So LeChâtelier's principle is simply putting that into place. So again, stressors are those that favor the formation of reactants or products. Remember, this means changing concentration, cutting up a solid, shifting the temperature. A catalyst does not actually cause a shift in equilibrium because a catalyst lowers the activation energy of both the forward and the reverse reaction. A catalyst simply allows you to arrive at equilibrium faster. So a catalyst is not considered a stressor and therefore is not governed by LeChâtelier's principle. So if I were to add more nitrogen gas to my Haber process, what would happen? The nitrogen gas would collide more often with the hydrogen gas and therefore produce more ammonia. So the reaction would favor the production of products. Our concentration of ammonia would increase while the concentration of hydrogen would decrease as it was used up to produce more ammonia. You can think of this in terms of collision theory. In fact, that is the preferred method for thinking of it. However, I know that not everyone thinks in terms of chemical collisions. So when I teach this in first year chemistry, I like to tell kids, think of equilibrium like a ball on a table. As long as the table is flat, the ball stays flat. So tables are made out of cinder blocks and a piece of wood. If I add more nitrogen gas, that's like adding a cinder block to one side of the table. Now when you lay your table down, your equilibrium, that ball is going to roll to the right. So it will shift to the right or favor products. In order to get the ball to stay on the table, to stay flat on the table, you and your friend would have to push on the table, right? So, you guys pushing is what happens to your reactants. The person on the left here would have to push down. The person on the right would pull up. So everything on the right, all of my reactants are going to decrease in concentration, while all of my products are going to increase in concentration. You can think of it in terms of a table, you can think of it in terms of collisions. I will explain both throughout the video. Just expect my table to progressively get faster and faster and messier and messier. If I were to take this reaction and add more ammonia to it, more ammonia means ammonia will collide more and more frequently, producing more products. So the concentration of ammonia after the initial increase will begin to decrease, and the concentration of nitrogen and hydrogen will increase. So the reaction will favor reactants or shift to the left as more and more ammonia collides, producing more products. From the table analogy, our table lays flat, we're at equilibrium. When we add more ammonia, that's like adding a block to the right side. So equilibrium shifts the left. In order to get the table to lay flat, you and your friend have to push and pull on the table to get it to lay flat. The person on the left, the reactants, is going to need to pull up. The person on the right, the products, is going to need to push down. So our reactants are going to increase in concentration. Our products will decrease in concentration. When we carry out the Haber process, ammonia is slightly heavier than nitrogen and hydrogen gas. It's more dense, so we are able to remove it through some density experiments. So if you were able to remove the ammonia from the reaction chamber, how would that shift the reaction? As ammonia is removed, less and less of it will be in the way of nitrogen and hydrogen colliding. And so more nitrogen-hydrogen collisions will occur. The reaction will favor the formation of ammonia or products. So the concentration of my ammonia after the initial decrease will increase, and the concentration of nitrogen and hydrogen will decrease. With the table analogy, removing ammonia would be like kicking a cinder block out from our table. With no cinder block there, our table no longer lays flat. Our ball of equilibrium shifts to the right. In order to get the table to lay flat again, everyone on the right will have to pull up. Everyone on the left will have to push down. Our reactants will decrease in concentration. Our products will increase in concentration. If we remove a reactant, less reactants means that there is less to get in the way of the ammonia colliding with itself, and therefore it will collide more often, producing more hydrogen and nitrogen gas. The concentration of ammonia will decrease as it shifts to the left, favoring reactants. From the table analogy, less hydrogen means you kick the cinder block out from the reactant side. Our table no longer lies flat. Our equilibrium will shift to the left. In order to get the table to lay flat again, our product side will have to push down. Our reactant side will have to pull up. So the concentration of reactants will increase as the concentration of products decreases. The Haber process is an exothermic reaction. Heat is a product of this reaction. Now, I wrote it in the equation. Please remember from our thermo unit that I could have just as easily written it this way, that the heat of reaction was less than 0. Or I could have given it to you as a numerical value, -92 kilojoules for each mole of reaction. Both express that this is an exothermic reaction and heat is a product. If it were a positive value, you would see that value as a reactant. Now, since this is an exothermic reaction, heat is a product, you can treat heat as any other reactant or product. If I heat this reaction up, that's adding another product. What happened when you added a product? Well, that heat is going to be used up by ammonia to collide more often, producing more nitrogen and hydrogen gas. It will favor the production of reactants as the reaction shifts to the left. From our table analogy, heat is just another reaction or product. So by saying I heated the reaction up, I added a cinder block to the product side. Equilibrium, the ball will roll to the left. In order to get the table to lay flat, everyone on the product side will have to pull down. Concentration of ammonia will decrease. Everything on the reactant side will go up. Nitrogen and hydrogen will increase in concentration. If an exothermic reaction is cooled, that energy needs to be made up. So nitrogen and hydrogen will produce more energy by colliding, so the reaction will favor products, or the reaction will shift to the right. So the concentration of ammonia will increase while the concentration of nitrogen and hydrogen decrease. From our table analogy, cooling the reaction down is like kicking the cinder block out for heat, so we have less on our product side or on our right side. Equilibrium will roll or shift to the right. In order to get the table to lay flat again, all of our product side has to increase, all of our reactant side has to push down, so the reactants decrease in concentration while the products increase in concentration. When we change the pressure of a gas system, gas only is affected. So when you have a reaction, you need to look at the phases if they talk about changing pressure or volume. Changing the pressure and thus changing the volume of a gas system will shift the equilibrium in one direction or another. When we increase the pressure, volume decreases, right? They are inversely proportional to one another. So an increase in pressure is a decrease in volume. With less space, the reaction will favor the side with less moles of gas. 1 plus 3 is 4 moles of gas versus 2 moles of gas. So the reaction will favor the side with less moles of gas when the volume decreases. That's because less space means these 4 will collide more often than these 2. So if the pressure increases, therefore volume decreases. 4 moles of gas is more than 2 moles of gas. The reaction will favor products or shift to the right. This is the time that you have to think about it and then write your analogy or draw your table based off what you thought. All right, since it favors the right, I'm going to draw my table so that the ball rolls to the right. So in order to figure out what happens, the concentration of my reactants decreases while the concentration of my products increases. If pressure decreases, that means volume increases. So you'll favor the side with more moles of gas. So in this case, the reaction will shift to the left, favoring reactants. The reason for this, with more space, the ammonias are more likely to collide with one another than 3 hydrogens and 1 nitrogen colliding, and therefore the reverse reaction is favored. From our table analogy, in order for our ball to roll to the left, it would have to look like this. Our product side would have to decrease, our reactant side would have to increase in concentration. On 14 and 15, here are some answers. Since the volume decreased, in each case we are going to favor the side with least moles of gas. 6 moles of gas becoming no moles of gas means that we will favor the side with no moles of gas, so shifts to the right for A. For B, 2 moles of gas producing 1 mole of gas, we shift again to the right, favoring the side with the least moles of gas. But what if they're the same, like example C, 4 moles of gas become 4 moles of gas? Well, that means that we're not favoring either side, so the reaction shows no change in equilibrium. In exercise 15, we are increasing the temperature on an endo and exothermic reaction. So when we increase the temperature on an endothermic reaction, that energy is used up to produce more products, so we shift to the right. In an exothermic reaction, that energy is used up by the products to produce more reactants, so we shift to the left. What happens to the value of K, however, is what number 15 asks. So the value of K is the ratio of products to reactants. So in A, since we produce more products, that means that the product value is going to increase. So K increases in exercise 15A. In exercise 15B, we produced more reactants. So the concentration of reactants increased. So the value of K decreases. That's why I told you that equilibrium position is related to temperature. Changing the temperature can shift the value of K. In fact, it's the only thing that will shift the value of K. With that, you are able to finish page 17 in your packet. I will see you next time. Next class, we will have a quiz. I will ask you to write the equilibrium expression, determine the reaction quotient, meaning I'll ask you, are we at equilibrium or not? If we aren't at equilibrium, you need to predict which direction the reaction shifts. Spoiler alert, probably not at equilibrium, so you need to tell me if it shifts to the left or right, favoring reactants or products. You will need to calculate Kc from Kp or vice versa, so you'll need to use that politically correct formula. Remind me to give it to you, as it is not on your formula sheet. And lastly, I will change something. I will provide some sort of stress, and you need to use LeChâtelier's principle to explain what happens in terms of collisions. Do I produce more reactants or products because of collisions in one direction or another? Next time, we will talk about solubility equilibrium. I will see you then.